Good good evening, good morning. I am Yumoto from the University of Tokyo. In this presentation, I'll be talking a little bit about our concept of a laser-induced breakdown spectroscopy package for the pressurized rover. Next slide, please. So just to remind you, laser-induced breakdown spectroscopy, or LIBS, is a method for element analysis. So in LIBS, we will shoot focused laser pulses to vaporize the part of a target, and with a spot size of approximately 300 microns. So very high resolution analysis are going. And we will measure the emission lines from the laser-induced plasma, like a photo on the bottom right. By doing analysis of the spectrum, we can predict or measure the elemental composition of the target by looking at the spectrum on the bottom left. Next slide, please. So probably many of you already know that the LIBS instrument has been flown on different multiple space missions, including NASA's Mars missions. So by NASA and the Chinese Space Agency's missions, LIBS has been demonstrated to have a rapid and remote measurement capabilities, and its capability yields a large amount of geochemical data. And LIBS advantage of the LIBS include, for example, rapid analysis. 100 spectra in 1 minute, so very fast. And LIBS can remove the surface regoliths that is covering the real composition of the sample rock. So this capability is particularly important for the lunar missions because the lunar rocks are typically covered by regoliths. So you can blow off the regoliths by a shock wave produced by the laser. And it's capable of a remote analysis up to several meters, so we don't have to really touch or get really close to the sample you want to measure. And finally, the LIBS can do a spot by spot analysis, which means we can measure grain by grain composition, mineral by mineral composition, and we can tell if the target is brecciated material or intact and homogeneous basaltic rocks or something like that. So collectively, these advantages of LIBS instrument is very useful for lunar missions. So if you go to the next slide, yeah, I am showing the science objectives relevant to the pressurized rover and our approach toward fulfilling these science objectives. So we are going to do in situ three-dimensional scanning measurements using a LIBS instrument in order to, number one, understand the volatile transport and storage processes in the surface and near surface of the lunar poles. And the second, we're going to use the LIBS to identify the elemental compositions and geologic end members of lunar polar materials. So as many of you already know, that there is water expected on the surface of the moon, and it migrates downward by the diffusion or pumping or sporadic eject burial. So drilling analysis and depth direction analysis by the LIBS laser pulses is important to identify the surface transportation mechanism of the water. And by scanning these lasers over the different local time of the moon, we can potentially identify the horizontal migration of the hydrogen or the water as the microcold trap, the position of the microcold trap changes. So by scanning these laser beams onto the sample, we can trace the behavior of water. So if you go to the next slide, Thank you. This is just to show you that we have developed the traceability metrics to the M2M objectives. So I'm not going to tell you a detail about this, but we have developed a set of requirements flowing down from the M2M objectives. Next slide, please. So I am showing two key results with our prototype to fulfill these scientific objectives. The first one is about hydrogen analysis using a prototype LIBS. So the paper published 2 years ago, we measured different kinds of materials, different kinds of lunar simulants containing different amount of hydrogen, and essentially we have done a calibration of hydrogen using those samples. And we found that we achieved the accuracy of 1/8% of water and 2 sigma detection limit of less than 0.5 weight% of water. So we think we demonstrated the water analysis capability of LIBS by this paper. And more recently, on the right-hand side, we have done small little experiments about the first layer detection on the moon by successively shooting laser pulses onto the sample. So in the middle, we have produced the hydrous layer sandwiched by anhydrous lunar regulus simulant. And on the right-hand side, we plotted the intensity of hydrogen peak as a function of number of laser shots applied to the sample. So what we found here is that the up to 100 pulses, laser pulses, we didn't see any hydrogen peaks, but as soon as we reached the hydrous layer sandwiched by the anhydrous layers, we started to see hydrogen peak. And as soon as it penetrates, we penetrate through this hydrous layer, we do not see the hydrogen peaks. So by such an experiment, we are now confident that we can measure surface and subsurface first layer by shooting laser successively. Next slide, please. The second key measurement results with a prototype is about the major elements analysis. So we did last year, the paper published last year, we did LIBS experiments for lunar relevant samples, including lunar meteorites, and essentially obtained a list of accuracies for different major elements using a LIBS. So the median relative error is approximately more or less smaller than 10%. And by plotting this amount of error onto the composition map of the relevant lunar geologic units, we can say that the sufficiently high accuracy is achieved to discriminate the rocks from major geologic units along the pressurized rover's traverse. So if you go to the next slide. Getting confidence from our breadboard prototype activities, we started to design and build our LIBS instrument. So our LIBS instrument is of course composed of laser and optomechanical systems that is including scanning mirror system and autofocusing actuator system. And we also, it does include the spectrometer and the imager with the CMOS detectors, and they are controlled by FPGA-based electronics. So the mass and size and the power are like this, and we can shoot the laser. Our experiment shows we can shoot a laser 50 centimeters away to 7 meters away of laser range, and of course, we have a strict crew safety considerations for this laser operation. Next slide, please. So potential cutoffs on the pressurized rovers is as follows. So we measure compositional variations along pressurized rovers traverse. So LIBS autofocuses samples several meters away, applies 100 laser pulses at 2 Hertz to probe regolith up to 10 millimeters in depth. And laser pulses scan the surface by gimbal to investigate horizontal composition variations. And by doing so, we can triage interesting rocks very fast to maximize science return per time. On top of that, we think we can enhance PR's operational safety and efficiency by this standoff geochemical analysis capabilities, because we don't have to really get close to rocks we don't need to approach samples every time. So I think this enhances operational safety and efficiency of the pressurized rover. Next slide, please. Okay, so LIBS instrument development status. LIBS EM is being built and integration will be going on this year and will be finished in September 2025. Next slide, please. Okay, this is a summary of my presentation. Thank you very much for your attention.